This is the first video on Nmr Spectroscopy, the main technique that we're going to be talking about in the unit on spectroscopy. I have an example of a proton and carbon NMR spectrum here. Spectrum singular, spectra plural. And you can see this sort of shapes of the peaks. Nuclear magnetic resonance needs certain kinds of atoms with certain arrangements in the nuclei to be able to be visible in the technique. We're fortunate that the proton, the normal abundant proton that exists in most molecules, is 99.98% abundant. So this isotope of hydrogen is visible in the NMR. There are other isotopes of hydrogen, like deuterium, that are invisible in NMR. We use deuterium actually usefully in the NMR solvents. If you think about it, your compound is dissolved in solvent to analyze in the NMR, and if the solvent was visible to the spectrometer, you wouldn't see anything but solvent signal. Your sample signal would be completely swamped in this sea of solvent. A common NMR solvent is chloroform, which has the molecular formula CHCl3. However, we replace the hydrogen with deuterium to use it as a NMR solvent, CdCl3. The signal for CdCl3 in the spectra on the left is here in the proton NMR. So this is a really concentrated sample where the CdCl3 signal is barely visible. In carbon NMR, the CdCl3 signal is right here, and it actually appears as a triplet of 3 lines there. So that's a little bit about the sample. Our focus really will be on interpretation of NMR data rather than on how the NMR instrument works. The key aspects of interpretation are shown here: chemical shift, equivalence and integration, and finally coupling and splitting. So beginning with chemical shift. Chemical shift is an indication of where in the spectrum from left to right the signals appear. Chemical shift is unique to different kinds of atoms in different chemical environments. So if you think about a proton in the center of an atom surrounded by a sphere of electron density. So here's electron density. The electron density shields the proton. And the implication is that it's shielding it from the NMR. So a normal, quote-unquote, proton that's normally shielded, for example, might be at 2 ppm, as shown here. There's your ppm units. That might be the value that you look up in a table for a certain type of hydrogen. The reason that the tables are not very useful, basically, is that you can have a phenomenon called de-shielding. So the normal proton is shielded if a certain phenomenon occurs to pull electron density. In this example here, your electron density, notice it's being pulled to the left away from the proton. This proton is now de-shielded from the NMR spectrometer, which has the effect of moving it or shifting it to the left, which is actually a higher frequency, technically speaking. So In the NMR normal scale of 0 to 10, de-shielded is further in this direction, and we sometimes call that downfield, whereas shielded is upfield in this direction. So it would be foolish to look up values in tables and try to just match them to your spectra because of the amount of shielding and de-shielding that goes on in molecules. De-shielding is often the result of an electronegative atom or group of atoms. So things that cause de-shielding: oxygen, nitrogen, sulfur, halogens like chlorine, fluorine, bromine, iodine. They're all electronegative. They pull electron density away from protons, and they de-shield, causing a shift to the left. Double and triple bonds have the effect of de-shielding. Aromatic rings, another one. A normal ring, like a cyclohexane ring, for example, this proton on a cyclohexane ring, or I should say these two, would be more de-shielded, but slightly, than on well, I drew a heptane, but on a similar kind of just linear molecule. Finally, there's this trend to notice, given everything else equal, in other words, similar de-shielding groups attached or shielding groups or whatever, a methyl is more shielded relatively, and a CH2 followed by a CH are more de-shielded. These last two are more minor effects. The effects of electronegative atoms are major effects. The next aspect of interpretation is equivalence, which leads to numbers for integration. Equivalence is often related to symmetry and to this concept of chemical environment. The best way to understand equivalence is to look at some examples. The 3 hydrogens on a methyl group are always equivalent. The reason being that they are never experiencing a different chemical environment from each other. And a big part of that is the fact that you have free rotation around the single bond of a methyl group. If you look at the molecule benzene here, which is an aromatic, all of the hydrogens in benzene, I think most people would deduce, are equivalent. You can sort of, they're all in the same plane. Remember, this is a planar molecule. That you can sort of twirl this around like a wheel. They're never in any different environment compared to each other. However, if I put a methyl group on either end of the benzene, and that should be a CH3, you can easily see that you now have different types of hydrogens. You have the 4 hydrogens on the ring and the 6 hydrogens on the methyl groups. And by symmetry, the 2 methyls are equivalent. And all 4 of the ring hydrogens are equivalent. If you look for a point of difference, say for this hydrogen right here, this hydrogen is 1, 2, 3 bonds away from a methyl group, 1, 2, 3, 4 bonds away from another methyl group. However, if you look at this hydrogen here, it's 3 bonds away from this methyl group, 4 bonds away from this methyl group. So really, you never find a point of difference between these 2 hydrogens. And the same goes for the ones on the other side. There's symmetry on both sides. So those 4 hydrogens on the ring are equivalent. You would expect in your NMR spectrum then to see a 6 hydrogen signal for the 2 methyl groups piled up, excuse me, and a 4 hydrogen signal for the ring hydrogens piled up, most likely at 7 ppm and 2 ppm. These numbers are called integrations, and they're just measuring just like in calculus, the integration, the area under a curve, under a peak, so all of this area is the integration of that peak. And you'll see integration written in different ways, but that's a subject for a later video. It represents the number of protons signals in that signal as a whole. More examples of equivalence. These two methyl groups are equivalent. So the 6 hydrogens are equivalent to each other. The carbons are equivalent to each other. We can do carbon NMR as well. And that's easy to see the symmetry there. The 3 examples over here on the right, these 2 hydrogens, they are the same with respect to each other and everything else throughout. They're equivalent, EQ. These 2 hydrogens are also equivalent. For example, this hydrogen is attached to a carbon here that's attached to a chlorine. Same for this hydrogen here. Both hydrogens are once removed from the other chlorine. Both those hydrogens are equivalent. However, these 2 hydrogens are not equivalent. That's also pretty easy to see because this hydrogen is attached to this carbon that has a bromine on it, while this hydrogen is directly attached to a carbon that has a chlorine on it. Excuse me. Cat jumped on the desk. So, here's another example. These 2 hydrogens, one coming front, one coming back, are equivalent because you have free rotation around these bonds. These 2 hydrogens are equivalent for the same reason. We know the 3 hydrogens of a methyl are equivalent. The thing I can point out here, though, is that these hydrogens here are not equivalent to these hydrogens here because these are closer to the OH group. So with the spectrum of this molecule, you would expect a 2 hydrogen signal of some sort, and then another 2 hydrogen signal of in a different place in the spectrum, and then the 3 hydrogen signal somewhere else. This is not intended to show where they would be. Rings introduce inequivalence a lot of times because you cannot rotate freely around the bonds of a ring. So notice these OH groups are both pointing up. They're on the top face of the ring. They're on the same face of the ring as these 2 hydrogens. So these 2 hydrogens, if you look at them and compare them in every way, are equivalent to each other. And then these 2 hydrogens here are equivalent to each other, but those 2 sets of hydrogens are not equivalent to each other. So A and B sets of hydrogens are not equivalent. We have one more example here. We know our methyl group hydrogens are equivalent to each other. These 2 hydrogens, again, back to being equivalent because of the free rotation. Whenever you have equivalent groups of hydrogens, remember, they pile up at the same chemical shift in the spectrum, and they would integrate for that number of hydrogens. Coupling and splitting, the last phenomenon to study for interpretation. Coupling is the phenomenon, splitting is what you see in the spectrum. The most common incidence of coupling is when you have a setup like this where you have a hydrogen here, for example, and a hydrogen here on the neighboring carbon. These hydrogens couple each other. Coupling actually occurs through bonds rather than through space, like this arrow implies. So the real coupling is occurring through these 3 bonds. 3 bonds is close enough for these hydrogens to couple each other. The effect of coupling, if we call this hydrogen A and hydrogen B, say you get a 1 hydrogen signal for hydrogen A, and a 1 hydrogen signal somewhere else for hydrogen B. We're assuming that they're not equivalent, and so they're at different places in the spectrum. If A and B couple each other, it leads to splitting. So the coupling leads to splitting. And therefore, proton B will be split once by its neighboring hydrogen, and A likewise will be split once by B. You would end up then seeing a doublet at each position, each chemical shift value. So a pair of doublets, I guess you would say. This is the most common type of splitting. I should say most common type of coupling, and it's called vicinal coupling. I believe I introduced the term vicinal earlier when I was talking about Newman projections, where we were looking at hydrogens on adjacent carbons in that situation as well. A much less common, but still not that uncommon, is geminal coupling. Geminal coupling would be coupling between these two hydrogens here, or more accurately, through these two bonds. Geminal coupling is usually in the case of rings, where if you look, for example, at the example right above here, where there's a top face and a bottom face, you might see geminal coupling between this proton and this proton. But it's less common than the vicinal type of coupling. I had one more example here of equivalence, and that is here. This is a good one too, because we can see that all three of these are equivalent. This one is equivalent unto itself. Now if I take this and look at it in terms of splitting, we would have a 1 hydrogen signal here and a 3 hydrogen signal here, and the 1 hydrogen signal would be split 3 times by each of its neighboring protons. So you'd have this initial signal split 1, 2, 3 times more, resulting in 4 lines total, or a quartet. So you have the initial signal split 1, 2, 3 more times by neighboring protons, resulting in 4 lines total. The 3 hydrogens for the methyl give you 1 initial signal here, split once by its neighboring proton, only 1, resulting in 2 lines total, or a doublet. So in your spectrum somewhere, you would have a 3 hydrogen doublet and a 1 hydrogen quartet. And we're going to continue splitting analyses at the beginning of this part 2 or the second video.